25% rule for motors is applied to single-phase motors rated 1 horsepower or larger, irrespective of the motor type. According to this rule, the motor's running load current must be multiplied by 1.25 to account for the starting inrush current. This applies to all single-phase motors, encompassing hermetic motors, multi-motor or combo load equipment, and cord and plug connected equipment. However, there is an exception to this 25% rule, specifically for motors that are a part of a hermetic refrigerant compressor. These motors do not need to have their running load current multiplied by 1.25 to account for the starting inrush current. It is possible that you are not factoring in the 25% rule for the room air conditioner motor. This can be a common mistake, as it may not be immediately apparent that the 25% rule applies to all single-phase motors. Overlooking this rule means you are underestimating the running load current of the motor, which can result in incorrect answers on an exam. To correct this, make sure to multiply the running load current of the room air conditioner motor by 1.25. This will give you the correct running load current for your calculations. To provide a more detailed explanation, let's break down the process of motor load calculations and where the 25% rule fits in. Firstly, identify all the motors that are part of the load you are calculating. This includes motors of all types, such as those used in air conditioning units, appliances, and other equipment. Secondly, determine the full load current of each motor. This information can typically be found on the motor's nameplate. The nameplate will list the motor's voltage, horsepower, and full load amps. Thirdly, apply the 25% rule to the largest motor. According to the National Electrical Code, NEC, you must increase the full load current of the largest motor in the group by 25%. This is to account for the motor's starting current, which is typically much higher than its running current. Fourthly, add up the full load currents of all the motors, including the increased current of the largest motor. This will give you the total motor load. Fifthly, add any other loads to the motor load. This could include lighting loads, receptacle loads, and any other electrical loads that are part of the circuit. Sixthly, size the conductors and overcurrent protection device for the circuit based on the total load. The conductors must be sized to carry at least 125% of the total load, and the overcurrent protection device must be sized to protect the conductors from overload. Let's look at an example. Suppose you have a circuit with 3 motors. The first motor is a 3 horsepower motor with a full load current of 17 amps. The second motor is a 2 horsepower motor with a full load current of 12 amps. The third motor is a 1 horsepower motor with a full load current of 7 amps. Firstly, identify the largest motor. In this case, it is the 3 horsepower motor with a full load current of 17 amps. Secondly, increase the full load current of the largest motor by 25%. 17 amps x 1.25 equals 21.25 amps. Thirdly, add up the full load currents of all the motors, including the increased current of the largest motor. 21.25 amps plus 12 amps plus 7 amps equals 40.25 amps. Fourthly, add any other loads to the motor load. In this case, let's assume there are no other loads. Fifthly, size the conductors and overcurrent protection device for the circuit based on the total load. The conductors must be sized to carry at least 125% of the total load. 40.25 amps x 1.25 equals 50.31 amps. Therefore, you would need to use conductors that are rated for at least 50.31 amps. You would also need to use an overcurrent protection device that is rated for no more than 50.31 amps. It is important to note that these are just general guidelines. You should always consult the NEC and other applicable codes and standards for specific requirements. Here are some additional tips for motor load calculations. Make sure you are using the correct full load current for the motors. The full load current can vary depending on the voltage and horsepower of the motor. Be sure to account for any other loads that are part of the circuit. This could include lighting loads, receptacle loads, and any other electrical loads. Use the correct size conductors and overcurrent protection device for the circuit. The conductors must be sized to carry at least 125% of the total load, and the overcurrent protection device must be sized to protect the conductors from overload. Consult the NEC and other applicable codes and standards for specific requirements. Let's delve deeper into the NEC requirements related to motor load calculations. NEC Article 430 covers motors, motor circuits, and controllers. It provides detailed guidelines for calculating motor loads, selecting conductors, and sizing overcurrent protection devices. Section 430.22 specifically addresses single motor applications, requiring that the conductors supplying a single motor have an ampacity of not less than 125% of the motor's full load current as determined by 430.6 AON. This 125% factor is the same as multiplying the full load current by 1.25, which is the basis of the 25% rule. For multiple motor applications, Section 430.24 comes into play. It states that feeder conductors supplying two or more motors must have an ampacity equal to the sum of the full load currents of all the motors, plus 25% of the full load current of the largest motor in the group. This is where the 25% rule for the largest motor becomes crucial in determining the overall feeder size. Article 440 addresses air conditioning and refrigeration equipment. While 430 covers general motor applications, 440 provides specific requirements for hermetic refrigerant motor compressors and air conditioning equipment. Section 440.22 states that the branch circuit conductors supplying a hermetic refrigerant motor compressor must have an ampacity not less than 125% of the motor compressor's rated load current or branch circuit selection current, whichever is greater. This requirement is similar to the 25% rule for general motors, but it uses the rated load current or branch circuit selection current specific to the motor compressor. Exception 2 of 440.22b addresses cord and plug connected equipment. It allows the use of conductors smaller than those required by 440.22 if the equipment is cord and plug connected and meets certain conditions. However, this exception does not eliminate the need to consider the motor compressor's load when calculating the overall circuit load. Annex D provides examples of load calculations, including those involving motors. These examples can be helpful in understanding how to apply the NEC requirements in practical situations. However, it's essential to remember that these examples are not exhaustive and may not cover every possible scenario. The examples in Annex D should be used as a guide, and you should always refer to the specific NEC sections for the complete requirements. Regarding the specific concern about balancing loads in single-family dwellings versus multi-unit buildings, the NEC does not explicitly require load balancing in the same way for both types of occupancies. In single-family dwellings, it's common practice to balance the load between the two phases of the service to ensure efficient power distribution. However, in multi-unit buildings, the load is typically distributed across multiple phases, and the focus is on ensuring that each unit has adequate capacity to meet its individual load requirements. The statement that the load balancing equation method only applies to single-family dwellings and makes no sense in identical multi-unit buildings is not entirely accurate. While the specific equation used for balancing loads in a single-family dwelling may not be directly applicable to a multi-unit building, the principle of load balancing is still important in multi-unit buildings to prevent overloading any one phase of the service. In summary, the 25% rule is a crucial aspect of motor load calculations, particularly for single-phase motors. It's essential to understand when and how to apply this rule to ensure accurate calculations and compliance with the NEC. When dealing with air conditioning and refrigeration equipment, pay close attention to the specific requirements in Article 440, and remember that the examples in Annex D are only a guide. Always refer to the specific NEC sections for the complete requirements. To recap the key points related to motor load calculations: firstly, identify all motors and their full load currents. Secondly, for single-phase motors rated 1 horsepower or larger, apply the 25% rule to the largest motor by multiplying its full load current by 1.25. Thirdly, for multiple motors on a feeder, sum the full load currents of all motors and add the 25% increase for the largest motor. Fourthly, for hermetic refrigerant motor compressors, refer to Article 440 and use the rated load current or branch circuit selection current, whichever is greater, and apply the 125% factor as required. Fifthly, consider any other loads in the circuit, such as lighting and receptacles, and add them to the total motor load. Sixthly, size the conductors and overcurrent protection devices based on the total calculated load, ensuring compliance with the NEC requirements. Remember that the NEC is a comprehensive document, and it's essential to consult the specific sections relevant to your application. The 25% rule is just one aspect of motor load calculations, and a thorough understanding of the NEC is necessary for accurate and safe electrical installations. In addition to the NEC requirements, it's also important to consider any local codes or regulations that may apply. These local codes may have additional requirements or restrictions that you need to be aware of. It's always a good idea to check with your local electrical inspector to ensure that your installation complies with all applicable codes and regulations. When performing motor load calculations, it's also important to use accurate and reliable data. This includes the motor's full load current, voltage, and horsepower. You should also use accurate data for any other loads in the circuit, such as lighting and receptacles. Using incorrect or unreliable data can lead to inaccurate calculations and potentially unsafe installations. It's also important to keep in mind that motor load calculations are just one part of the overall electrical design process. You also need to consider other factors, such as voltage drop, conductor dirting, and overcurrent protection. These factors can all affect the performance and safety of the electrical system. By carefully considering all of these factors, you can ensure that your electrical system is safe, reliable, and efficient. In conclusion, the 25% rule is a fundamental aspect of motor load calculations that must be understood and applied correctly to ensure compliance with NEC and safe electrical installations. Remember to identify all motors, apply the 25% rule to the largest single-phase motor, consider hermetic refrigerant motor compressors separately, and account for all other loads on the circuit. Always consult the NEC and any local codes or regulations for specific requirements, and use accurate data in your calculations. By following these guidelines, you can confidently perform motor load calculations and contribute to the safety and reliability of electrical systems. The NEC is updated regularly, so it is important to stay current with the latest edition. The NEC is published by the National Fire Protection Association, NFPA, and is available for purchase on their website. The NFPA also offers training and certification programs for electricians and other electrical professionals. These programs can help you stay up to date on the latest NEC requirements and best practices. Remember that electrical work can be dangerous, and it's important to take all necessary precautions to protect yourself and others. Always de-energize circuits before working on them, and use appropriate personal protective equipment, PPE, such as gloves and safety glasses. If you are not comfortable working on electrical systems, it's best to hire a qualified electrician. A qualified electrician has the training and experience to safely and effectively install and repair electrical systems. They can also ensure that your installation complies with all applicable codes and regulations. Taking the time to understand and apply the 25% rule correctly is essential for safe and compliant electrical installations. It demonstrates a commitment to safety and professionalism in the electrical industry. Keep learning, stay informed, and always prioritize safety in your electrical work. To further clarify the application of the 25% rule, consider a scenario involving a small commercial building with several motor loads. Firstly, there's a 5 horsepower single-phase motor for a water pump with a full load current of 28 amps. Secondly, a 3 horsepower single-phase motor for an exhaust fan with a full load current of 17 amps. Thirdly, a 1/2 horsepower single-phase motor for a small circulation pump with a full load current of 5 amps. Fourthly, a hermetic refrigerant motor compressor in an air conditioning unit with a rated load current of 12 amps. Firstly, identify the largest single-phase motor, which is the 5 horsepower water pump motor with a full load current of 28 amps. Secondly, apply the 25% rule to this motor. 28 amps x 1.25 equals 35 amps. Thirdly, sum the full load currents of all the other motors, excluding the largest single-phase motor and the hermetic refrigerant motor compressor. 17 amps plus 5 amps equals 22 amps. Fourthly, add the increased current of the largest single-phase motor to the sum of the other motor currents. 35 amps plus 22 amps equals 57 amps. Fifthly, consider the hermetic refrigerant motor compressor. Since it's a hermetic motor, you'll use its rated load current of 12 amps, but you don't need to apply the 25% rule to it unless otherwise specified by the NEC or equipment instructions. Sixthly, add the hermetic motor compressor's current to the total motor load. 57 amps plus 12 amps equals 69 amps. Seventhly, if there are any other loads such as lighting or receptacles, add them to the total motor load. For example, if there's a lighting load of 20 amps and a receptacle load of 10 amps, the total load would be 69 amps plus 20 amps plus 10 amps equals 99 amps. Eighthly, size the conductors and overcurrent protection devices based on this total load, ensuring compliance with the NEC requirements for conductor ampacity and overcurrent protection. Remember to consult the NEC for specific requirements related to conductor sizing, overcurrent protection, and any applicable directing factors. This example illustrates how the 25% rule is applied in a practical scenario involving multiple motor loads, including single-phase motors and hermetic refrigerant motor compressors. By following these steps and consulting the NEC, you can accurately calculate motor loads and ensure safe and compliant electrical installations. Another important aspect of motor load calculations is understanding the difference between continuous and non-continuous loads. A continuous load is defined as a load that operates for 3 hours or more at a time. Non-continuous loads, on the other hand, operate for less than 3 hours at a time. The NEC requires that conductors and overcurrent protection devices be sized differently for continuous and non-continuous loads. For continuous loads, the conductors must be sized to carry at least 125% of the load current, and the overcurrent protection device must be rated at not less than 125% of the load current. This is to account for the fact that continuous loads generate more heat than non-continuous loads, and the conductors and overcurrent protection devices need to be able to handle the extra heat. For non-continuous loads, the conductors and overcurrent protection devices can be sized at 100% of the load current. However, it's still a good practice to oversize the conductors and overcurrent protection devices slightly to provide a margin of safety. In the example above, if the water pump motor and the exhaust fan motor are both considered continuous loads, then the conductors supplying these motors would need to be sized to carry at least 125% of their full load currents. This would result in a larger conductor size and a larger overcurrent protection device. It's important to carefully consider whether a load is continuous or non-continuous when performing motor load calculations. This will ensure that the conductors and overcurrent protection devices are sized correctly and that the electrical system is safe and reliable.